good morning, everyone, at least those of you who are in this time zone. Welcome to today's Cobolt Laser Lounge webinar. Thank you very much for joining. My name is Håkan Karlsson. I am the CEO of Cobolt, and I'm sitting here together with
Peter Jannes. I'm product manager.
And Peter and I, we are sitting in an extraordinary gray Stockholm. It has been very cloudy here for a long time period. I saw in the news yesterday that the record number of hours that we have seen sun through the cloud cover here in Stockholm in December is a solid 0.0. So a little bit depressing. And this is because it's so much warmer here than usual. It's been the warmest November ever recorded, and December is probably going to be the warmest ever recorded month or December in Sweden too. So it's quite dramatic how the climate has got warmer here in Stockholm or in Sweden over the last couple of decades. And so instead of having snow at this time of year, we're instead having warm weather and a very solid cover of clouds, which is not so funny. But enough about that. If you didn't know it before, you know it now. It's a strong Swedish tradition to complain about the weather and climate change, right?
Yeah, true.
But we're also very happy today. We have a guest speaker with us here today at this webinar in France. We are having Valentina Caorsi. Good morning, Valentina.
Good morning, everyone. Good morning. Thanks for the invitation. Happy to be here from Paris.
Yes,
and,
you're in
yeah.
Paris. And how are things in Paris? Are you seeing any sun down there?
Well, yeah, sunny. Yes, we have been seeing some sun, even though Paris is quite gray as well, but not as you were describing about Stockholm. Not that sure, but
we're not counting sun hours here. We're counting sun minutes. So
yeah, that's hard.
But very much welcome. We're very glad to have you with us today.
Thanks again for the invitation.
Valentina is from abbelight, a provider of solutions of super resolution microscopy. And she's going to talk today about her and her team's latest development in making multicolor stochastic reconstruction microscopy using single color red laser.
Yes, exactly.
I should also say a few words about the format of this webinar for those of you who haven't been joining this before. So this is our own digital platform to try to reach out to our community to talk about new products, new applications, or anything else in photonics that we think is interesting to share now that we are not able to go to conferences or trade shows. And we're trying to keep the format to something like a coffee break seminar, even if I understand that not everyone is on coffee break time zone right now. So we try to keep it at maximum 30 minutes, including questions, and we hope to open up a discussion at the end of the presentations. So feel free to try to type in at the bottom of the dashboard down here. You have a chat box, and you can type in questions during or after the presentation, and we'll try to go through them afterwards. So feel free. Any question is possible to ask. Before we hand over to Valentina, we're going to say a few words about the laser that she and her team has been using in this work, which is a new Cobolt laser that looks like this. It looks very much like most of the lasers we make at Cobolt, but it's actually part of a new product series, which we call the Cobolt Rogue red laser. And it's a little bit special. It's confusing because it's both single mode and multi-mode. And I thought I'd ask Peter to give some more information about what is this laser.
Yes. So let's see if we can get the slides up. So as Håkan said before we leave the word to Valentina, I will just mention a few things about the Cobolt Rogue. It is a continuous wave diode pump solid state laser. The Cobolt Rogue 640 nanometer obviously emits at the wavelength of 640 nanometers. It is high power, emitting 1 watt of optical power. And what differs with these lasers compared to most of the Cobolt lasers is that it's longitudinally multimode. That means that it has a wider spectral bandwidth, just below 150 gigahertz, or a little less than 200 picometers, if you want to express it in wavelengths, which makes it not suitable perhaps for interferometric application, but very well suited for applications where the single mode behavior is not necessary, like for microscopy, for instance. So although it's longitudinally multimode, it is transversally single mode, which means that it has a perfect TM00 beam, as you can see on the bottom left, with an m² value of less than 1.1. Making it very suitable for applications where the beam quality is important, or if you, for instance, would like to fiber couple it into a single mode fiber with very good coupling efficiency. So although it's a new series of lasers from us, it still shares the same optomechanical platform as our well-established 0501 series lasers, which means it has the same stability and robustness as that series of lasers, which is sort of illustrated with these two plots here. On the upper right, you can see typical power stability measured over a time of 8 hours, where you can see that the power varies well below 1%. And you can also see that it has a nice, stable low noise performance. On the bottom left, you see how it performs when you stress the laser during a temperature cycling. So you can see the red curve showing the temperature variation from 20 to 50 degrees Celsius over a time period of 12 hours, 2 cycles. And as you can see in the blue curve, it still has a very good power stability even under these conditions. And finally, I just want to mention that it's available with 2 mechanical configurations. On the upper right, you see the standard configuration with most of the electronics contained in an external controller, having a very compact laser head, but it's also available as a standalone laser head with all the control electronics integrated in the laser head, making it only 2 centimeters longer. So it's still a very compact solution. Available is also a lot of accessories. We have heat sinks. We have heat sinks prepared for external fiber coupling, or we can also provide fibers and fiber couplers. And it's also compatible with our laser combiner should you need more wavelength in a combined beam or into the same fiber. I think I'll leave it at that.
Okay, thank you very much, Peter. So this is, as Peter said, it's a single transversal. Yeah, okay. Presentation. So it's a single transversal mode beam, very good, but multi-longitudinal mode, so we get a little more power in the red. And now I will thank you very much, Peter. Try to hand over to Valentina, and I'm very excited to hear what you've been doing with this laser for your microscopy setup.
Yeah, thank you. Thanks again.
Yes, here we have some beautiful pictures.
Yeah, can you see them? I think the presentation. Yeah, perfect. So thanks again for the invitation. I'm really happy to be here in this lounge. Well, I tried to keep it quite informal, as in theory this sort of platform would love to be, even though, of course, being in remote gives not that interaction that could be usually possible over a coffee. But please, if there are questions, even though while I'm speaking, just write or try to raise your question, and we'll be happy to stop and discuss. So as I've been already introduced, I'm working for Abbelight, and Abbelight is a company that deals with nanoscopy. So first of all, as I don't know how many of you in the audience are into this kind of techniques, I just wanted to briefly tell you what's the meaning of nanoscopy. So what is a nanoscope? So here you see an image. I can tell you it's quite horrible now that I see also the projection but let's say that this is an epifluorescence image. And so what you could do with a nanoscope is to diffract to overcome the limit of the diffraction barrier and really go to unravel the details of the structures. Here you see clustering, which are structures within a cellular environment. So this is what abbelight is focusing on, and to reach this kind of improvement in resolution and in capability of getting such fine details, we are focusing on single molecule localization microscopy. If you have never heard of it, the principle is quite easy. Instead of having the fluorescence that is coming out of your samples from everywhere, you will try to switch on a single molecule so that you can separate their emission in space and in time. And so here you see, for example, what we usually call blinking is this phenomenon for which you see then the molecule that go from an off state or dark state to an on state where they are really emitting fluorescence. And if we are good to do this separation in space and time, then we would be able to detect the text, the single molecule, use some mathematics to find their center in X, Y, Z, the photon numbers, so that we can precisely then put their localization. And the image in the end is the reconstruction of this stochastic emission process. So I think that even though I don't want to enter into all the details, but I think that already from just this overview, there is a lot that is going on between this kind of microscopy technique, which is indeed not only hardware, but it's also chemistry and biology, so to permit the molecules to go from this on and off state, and also a lot of course, software, because we need a lot of processing of the data. And abbelight is really focusing in each steps of the imaging workflow. So with solution that helps the preparation of samples up to the imaging, so with the hardware and software, also up to analysis of the single molecule localization data. So today, as mentioned, I wanted to enter the one particular aspect that we've been working a lot recently to try to give, to improve even more our product, and so to give, I would say, a fourth dimension to a nanoscopy image, as you could see here, that we could have an XYZ information, but what if we could also give some colors, so having also lambda information. And the main limits of single molecule localization microscopy to access multicolor nanoscopy is really that the characteristic to switch on and off the fluorescent molecules depends, of course, on the fluorescent molecules, and this change from color to color. This means that, for example, the chemistry also needed changes. And this hampers to really properly do quantitative single molecule localization microscopy with fluorophore that switch on and off in different spectral range. Of course, as well, chromatic aberration. Chromatic aberration at the nanoscale. Here we are talking about the possibility to localize molecules with a precision of 10 nanometer. So you can really understand that it becomes quite significant at this range. And up to now, the most common solution to do multicolor imaging is sequential recordings of one color after the other. And so there is also the problems of drift on this long session of measurements. So within abbelight, we thought why we could try to use and focus fluorophores that are all in the same spectral range. And here we choose the red and far red. You can, I think, imagine already that if we are able to put these fluorophores that are all in the same spectral range, we are already gaining the fact that the photoswitching characteristics are quite similar, and of course we reduced quite to a neglectable level the chromatic aberration. And so this is what we are doing. So we are choosing the 3 fluorophores. You see here the emission spectra of the 3 fluorophores that we usually use, the 647, 660, and 680. So you see that are separated of between 20 and 40 nanometer. And so now the beauty would be to being able to acquire simultaneously the fluorescence of these 3 fluorophores and being able to separate their emission. So how we can do it, because the proximity of in terms of wavelength is quite tight. Well, the idea is easy, and it's a well-established technique, and I think I also quite old, is ratiometric imaging. So we are inserting a dichroic mirror, and we collect the emission light on 2 cameras. So what you can see here, for example, that we can detect on camera 1 all this portion of the emission spectrum, and on camera 2 all this portion of this emission spectrum. Of course, we are collecting single molecule. So you can see here an example. And then, so what we can do is that we can do a ratiometric analysis. So if we do the ratio of the PSF collected on both cameras, this will be the lambda identity card. So it will be really a signature of the detection on which fluorophore it is assigned. Let's assume an easy examples. If I see that 50% of the photons are collected on camera 1 and 50% on camera 2, more or less I would say that is 660. If it is, I don't know, 80% and 20%, it will be 647. The opposite, 20% and 80%, it will be 680. So by doing this ratiometric imaging detection per detection, then we can obtain this. This is the distribution of the photon ratios. And now you see here clearly that we observe 3 populations. So I can distinguish, and now the game is done, because what I just need to do is to assign these different peaks to the 3 fluorescent molecules that I choose. And now I can access colors, and I can give colors to my nanoscopic information. So this is already great, and this is our newest product that we have been launching, the Safe RedSTORM. But I wanted to highlight also another aspect that is common to all abbelight products, but in this condition is even more useful. Maybe you already noticed if you're familiar with the technique, but if not, let me tell you that the usual standard in the market in terms of field of view is quite reduced. As you can see here, is in the best case scenario is around 50 by 50 micrometer. In most cases, it's more around 25 micrometer by 25 micrometer. So even half of that. And as you can see, we are giving the possibility to do this nanoscopy multicolor and access this multicolor nanoscopy information over a huge field of view of roughly 200 by 200 micrometers, so exploiting all the chip of the CMOS camera. And this is thanks to a technology that we have been implementing that is called ASTER, and is trying to avoid the problem of Gaussian illumination. So if you see here, as you see here, if you have a Gaussian beam that is illuminating your samples, you induce, of course, different blinking depending on the region in the field of view where you are. So you have really good blinking possibilities at the center, and by good blinking I mean that you have a really nice single molecule regime that of course it worsens the more you go towards the edge. And so the idea behind is to, instead of using a Gaussian beam to illuminate all the samples, we reduce a little bit the size of our Gaussian beam and we scan rapidly the Gaussian beam so that we arrive to have a flat top illumination. And this gives a real homogeneous excitation so that they can be really exploited, particularly with single molecule localization microscopy. And so this is why now we can really improve the capacity of our instruments. So what I really want to highlight in this case is that, of course, you can imagine that if you want to excite all the molecules that are present here at this level on a big field of view, and if we want to access the multicolor nanoscopy, that means that we have 2 population or 3 population, it will be quite a dense environment. And of course, these 3 parameters means that we have a big requirement, which is the power output that we need. And this is why we are now together with Cobolt today to show really the advantages of using such a laser to really induce over a big field of view the single molecule regime and being able then to acquire multicolor nanoscopy images. Here I'm showing you just how the localization precision, thanks to disaster technology, and then gives really then a quite good homogeneity in localization precision, as you can see here, over a large field of view. And I think with this, I'll finish. Just that I think I already gave you a lot of information. I think it's better maybe to have a space for questions. Let me just summarize what I've been presenting in these 4 words. Now, it is a really interesting product because now you have only 1 laser, 1 powerful laser, 1 buffer, 1 acquisition, but you get 3 colors on this huge field of view with nanometer precision. So thanks again, and thanks for being present today.
Thank you so much, Valentina. It was a great presentation, super interesting, very exciting, very impressive. So nice multicolor super solution images with just 1 laser. Very impressive. So we have a couple of questions. And again, those who are listening, please feel free send in any questions you might have regarding the laser or the work that Valentina and her team have been doing. I have 1 question for you. Do you have any particular end user application in mind where you think that this multicolor super solution STORM is particularly of interest?
Well, we have many applications. Well, you saw already on the last slide that put a neuron. So neuroscience is usually a good target, but I would say that there is no limit in which could be the biological applications. The point is having the good questions, usually, of course, linked to possible structures, as this kind of technique, the single molecule localization microscopy technique, allows to reveal the fine structure of biological samples. It could be also not biological. We can also extend it to materials and other kind of samples. As a background that is a little bit more on the biophysics, I usually tend to go always over a cellular environment. But we can extend this technique to also other kind of materials. And surely the fact to have different structure, the possibility to see simultaneously different structures within the same environment, of course, open the ways to many applications.
Mm.
Yeah.
So neurology is a field of particular interest.
But as well, for example, I can say mechanics, adhesions. I would say cell biology in general. We have application in many subjects. Yeah.
And biologically, is it easy to have these multiple fluorophores that are similar in spectral properties to bind to different types of biological structures?
Yes, this is a good question indeed, because I didn't put it, but it's quite an important aspect. But it's quite easy because, like, let's say that the most common, I don't know, GFP, cherry protein that usually researchers have already in their cellular lines could be easily tagged with this nanotag that carry then these fluorophores. So, and this will allow to switch on the nanoscopy information then by targeting this. But it's quite easy indeed to use, for example, nanotag or to fragment of antibody to target your protein of interest or the structure that you want to label. Yeah.
Okay. Another question that will come in here is about the microscope. Does this technique require any speciality in the microscope setup?
No, the microscope indeed can. This is indeed you see. Maybe I don't know if you want to share again the screen. Just a second. Okay, sorry. So, and you see also here now. You see the module then.
Yes.
Okay, perfect. Okay. So here you see.
Yeah, we see the last. Yes, exactly. Sorry, I have something covering. Yes, we do.
Okay. Okay. So now this module is really is going to be is an external add-on to any inverted microscope. So the answer is easy. This is the module that allows to turn any kind of epifluorescent microscope into a nanoscope. And we completely control the microscope in terms of X, Y, Z focus and everything. So everything can be done and controlled by our software.
Okay.
And there is no limit in the brand that can be used.
Okay. And here is the question for you, Peter. What would you say is the difference between this type of red laser from other types of lasers in this spectral range, for instance, diode lasers at this range?
Compared to a diode laser, it is the power is significantly higher. The beam quality is significantly better, and also there is a much higher precision in the wavelengths. I mean, all our lasers are sort of hit the target wavelength very precisely.
And this is because it's a diode pump laser.
Yes, it's a different laser.
Valentina, another question for you here.
Yeah.
To integrate this laser, how do you need to control the laser in any special way, like for instance synchronizing it with the detection or modulating it at high speeds?
No, this is we did it by fiber coupling, and then we control the laser power, and this can be indeed controlled by abbelight software, and then we synchronize the camera with this Aster technology in order to scan. So there is a scanning process now to get this homogeneous field, but this is done by the software. Of course, the user can the experimented user have access to parameter to play as well with the modalities, or otherwise it will be easily guided by the preset of abbelight.
Okay. And another one regarding the field of view.
Yeah.
What is the total field of view you can image, and how long does it take to image? Oh, that sounds an interesting question.
Yes, okay. This indeed is quite a good, I think, a parameter because, okay, the field of view, now the limit is really the chip of the CMOS camera. So I would say 200 by 200 micrometer, depending also on the connection that you have to the microscope. So if you have a C mount a connector, you will reduce because you will actually the C mount connector will be smaller now than the chip of the camera. So it will be maybe around 150. With an F mount, you will cover completely the entire chip. So the limit is really the chip of the camera. To the first answer. The second part is quite. You have quite a lot of flexibility. So if you want to acquire the entire field of view, is not changing the speed that you can. Right, it's changing the speed, but on the good side. Let's say that to acquire a good field, an eye field of view, you can scan at I don't know 20 millisecond per frame. And then you have the entire field of view. So depending on which is the biological question, you can really switch by doing a little bit slower acquisition on such a big field of view, or reduce the size of the image, but increasing then the speed, because you can even go at 400 or 500 frames per second on maybe 25 by 25 micrometer. And so again, this is really the flexibility of having this Haster technology, because you really can tune how you want to excite your molecules, and so you can really go at high speed, but of course on smaller region. In the neuroscience, for example, case, sometimes it's the best option to do smaller region to really find the real protein of interest. On a cellular example, as it was, for example, for looking at tubulin or other sort of similar structures, it might be instead more useful to have a really huge field of view, where you will have then the information that is already in one single acquisition. You will have the statistic of, I don't know, 10 cells. So it really depends on which is the questions at the beginning. But the beauty is that you have this versatile illumination that you can tune depending on the need.
Okay. Okay, thank you very much, Valentina. We are running out of time, so it's time to round. So I'd like to thank you so much again, Valentina. It was super interesting to hear your presentation.
Thanks again for the invitation. It was nice to be here today. Yeah.
And thanks to you, Peter, for talking about this new red laser. And thanks to all of you that have been listening today. Thank you very much. And please, if you have further questions, don't hesitate to send us an email through our website or to Valentina, to abbelight, and we'll get back to you afterwards. Thanks again for listening, and have a nice holiday season coming up, and a happy new year. Thank you, and bye.
Bye. Bye. Bye. Bye. Bye.